Okay. So, welcome everybody. Thank you all for being here today. It's a pleasure for me to be the chair of this session of the SISSA Women in Mathematics this year. So, first of all, I would like to introduce a bit why we are here today. So, basically, the main reason, as you may know, as you may understand from the title, is to celebrate women in mathematics. And of course, you know that there are a lot of problems, a lot of issues for this topic. So we are here also to discuss these problems. And I would like to underline that this is a dedicated space to discuss why there is a few female presence in our field, so in STEM in general. I don't know how many people already know what STEM is, but it's just science, technology, engineering, and mathematics. So the full science, say, field. And so why did we decide to do the SISSA Women in Mathematics this day, so on the 13th of May? The reason is that May 12th is the birthday of Mariam Mirzakhani. She was the first woman to win the Fields Medal, and you know, the Fields Medal is the like the Nobel in our field, so it's the main award that can be won. Of course, May 12th was Sunday, so we are here today. It is Monday, 13th of May. Okay, so as I said before, there is a problem in the sense that there exists a gender gap in our field, and indeed, you see here that the only two women that won the Fields Medal are Mariam Mirzakhani and Marina Gazowska. I hope that this is the right pronunciation. But I mean, two women in a lot of years is a small number. So we are here to discuss why this happened. So I'm very happy to have today with us these three speakers. So we have Professor Valentina Beorchia from University of Trieste, Professor Valeria Chiadò Piat from Politecnico di Torino, and also Dr. Maria Strazzullo from Politecnico di Torino. I think most of you know already Maria because she graduated just 2-3 years ago. Three. Okay. So maybe you already know her. So the schedule of this afternoon is this one. So we will have, first of all, a panel where we will discuss, as I said, the problem of the gender gap. So we will start now with this panel discussion. Then we will have the coffee break at the ground floor, and then the scientific seminars of our three speakers. So I stayed large with the timeline, so maybe we will finish a bit before, but yeah, around 5:30. Okay, so let's start with the panel discussion. Okay, what I thought, maybe stay here. Okay, what I thought for this panel is to do like an excursus through the stages of the whole academic career. It's a new format for this SISSA Women in Mathematics, so I hope you like it because it's totally my fault if you don't like it. Since our career is based on data, I think data-driven is the most frequent expression in our talks. So I would like to provide you some data about the gender gap in our field and provide you how this data vary during the career advance. So from the bachelor master degree to the PhD to non-permanent and permanent positions. So the tenure track and full professorship. Okay, and I will do it in a, say, new way. So I would like to propose you some quiz. It's very easy, of course. So you just have to scan QR code. It's done using Slido. So I don't know if you are familiar with this framework, but you will just have to scan a QR code and you will access the quiz. Okay, then of course we will have with our speakers a discussion, an open discussion, and in particular we will focus on the reasons why women may be encouraged or discouraged to continue the academic career. Okay, so of course it's totally interactive, so you can interrupt me whenever you want. You can also from home, you can unmute yourself and do questions. And also the speakers, of course, if you want to interrupt me. And okay. So we start from the first stage, so bachelor master degree. Okay, the first question that I would like to ask you and to, of course, discuss together is what are the female-male attendance percentages in higher education in Italy? So what does it mean? I will provide in the quiz two percentages. One is for female and one for male. And these attendance percentages mean basically what are the percentage of female that choose to go to university after the secondary school. So basically, if we have here the 40%, means that the 40% of female wants to go to university, and for example, the 30% of male wants to go to university. Okay, just this.
Is this only concerned to STEM?
No, it's global. It's for all the
in general.
Yes, higher education. So just after secondary school, go to whatever university first. Okay, so let's scan this QR code. It should be easy. So if you have problems, you should just tell me. Of course, the speakers can also, say which are the percentages that they think are the right one. Okay, so the first percentage is for female, and the second one is for male. Just a little bit of time to answer. So basically, if we have a 20% for female and 50% for male, it means that the 20% of women wants to go to university, and the 50% of male go to university. So the sum does not have to be the 100%, of course. Okay, once you are done, you can just raise your hand so that we can continue. Okay, so I see that everyone did the quiz. Okay, so yeah, you were close. Okay, okay. Okay, so the right answer was the second one. So basically, how we can comment it? I mean, the data. Data says that the 41% of female wants to go to university, while the 29% of male wants to go to university. So basically, female students, women, are more inclined to study at university. And you can see this data. Okay, now, sorry. Okay, you can see this data here, basically. So this is like an evolution through the years. So here we can see the data for the 2006, 2011, 2016, then 2021. More or less, I would say that the proportion is still the same through the years. But we start from this statement. So women in general are more inclined to study at university. Okay, let's go through the second quiz. Okay, so the second quiz, you have to stand for again, sorry for this, but basically, what is the percentage of female graduates, so female students in STEM? So now we are in STEM, and you can see two different percentages because one is for bachelor and one is for master programs in Italy. The percentages are for 2019, so it's a different year because I found this data. But basically, it means that, for example, in a bachelor, the first answer means that in a bachelor degree, we have the 26% of female students, and in a master, the 41%. Okay. So just wait a bit. So I don't know what, for example, Valeria, Maria, what do you think is the right answer in this case?
It's really funny because actually Anna showed me the slide and I don't remember the
but I didn't say the right answer.
I mean, I think that it's
so it's a memory quiz for you.
yes. My memory told me something like the first one, so no. 26 is quite low, but okay, 36-41.
Okay, then it's the right answer. Okay, so I mean, I was it was difficult because the percentages are close, okay, to each other. So yeah. And if we see some graphics, some plots, we can see that basically, yes, the solution is 36% for bachelor programs. This is the evolution of this percentage through the year from 2013 year to 2019. You see that basically nothing is changing from years. So female are still underrepresented, but I would say that the percentage is quite high, so it's close to, it's not so small, I would say, okay. And for the master degree, it's a bit higher, so we are well represented in master programs. And a fun fact is that the average of the European Union is smaller than in Italy. So in the European Union, the average is the 32.5%. So we're doing better than the average. Okay, here, no quiz for now. I would like just to show some details on how this percentage is distributed throughout different areas. So biology, physics, mathematics, and engineering. So the red line here is for biology and related science. Okay. Then the blue one is for physics, the yellow one is for mathematics and statistics, and the green one is for engineering. And here you see basically the evolution throughout years. This row here is for 2013, and this row is for 2019. So the evolution was in this direction. So basically, you see that there is a difference also inside the STEM category. So for biology, we see that a percentage that is 70%. So basically, a lot of women want to do biology. And for example, for engineering, we see like more or less 25%. And okay, I would like to comment also this with you, in the sense that my opinion, but of course it's my opinion, is that still we have in our society like a cultural believing that engineering, informatics are for men. And for example, psychology, also neuroscience, maybe, since here at SISSA also we have neuroscience, and I don't know, biology is for women. So what do you think about this?
Yeah, maybe you're right that there are for sure some prejudice, if you want, I think, in the society. But when I look at these graphs, it comes to my mind also the fact that we should improve the, let's say, the balance, not only at trying to show, for example, to girls that it's nice to do mathematics, but also saying to boys that it's nice to study literature, I don't know. So to really go towards a person-dependent choice and to leave people free from this kind of stereotypes. That would be important for me.
Yeah. So I think, yes, that especially in Italy, the stereotypes that you mentioned, they were very present, but maybe nowadays with the new generation, maybe they are just less present. I think that nowadays the most important problem is the future, the possible career. So maybe I can imagine maybe for female is more attractive biology because it is simpler to find some also research work in a private center or somewhere else. No? So the academic career is very, very hard nowadays. And the students of this last generation that I met told me that females especially are scared by the difficulty of having a career. So I don't know. So I'm not sure that now the young girls, but I would like also to hear somebody from which are younger than me. I don't know that if they really feel these stereotypes, but rather other problems.
Okay. Personally, I would like, first of all, to relate a little bit with the comment of Valeria. These kind of events, actually, I think that are totally, let's say, almost totally thought for men audience, like male audience. I mean, we need the support of male audience in this kind of setting because the first thing, I mean, at least, I didn't feel the pressure and I was somehow, yes, encouraged by my family that I was able to do the career that I wanted. And this is totally true. Like, I never felt different from a male. But for sure, there is some kind of social pressure that I feel that men usually do not feel, I think. And I believe that the way to grow in this setting is actually to focus on how we grow little boys. Because, I mean, we know now that we have to grow little girl with confidence, but I think that the message that should pass is that we have to grow the boys through, kindness and sensitiveness, Yes. So I think that this is the first thing. So I'm really happy here to see a lot of male faces, okay, in the audience. And I mean, you should be able to help us in this path, okay? Because we need your support. This is very important for us. And I really believe that these percentages are strongly related to the fact that men have to, play with cars and enjoy building stuff, while women has to, dress Barbies, but I love dress. I mean, I love dress Barbies too. So it's not really so strong related, but still there is some kind of social pressure to, to deal with.
Okay, so basically you think that we should act even before, so in not childhood, but I would say in secondary schools, maybe, say primary, secondary schools, high schools. I mean, we have different also opinions, so it's good to see that there are also. And if we go to, this was for bachelor programs, if we go to master programs, I would say that the percentages for engineering surprisingly increase a bit. For physics, mathematics, maybe also for mathematics increase a bit. For biology, still the same. So then in master students, we have somehow more intention to hear, according to data, of course. I mean, we have a bit more intention to stay at university for STEM. Of course, we saw also the percentages in average were quite close. So we had like 36%, 41%, so quite close. But I would say that these percentages are still high because we will see. You will do other quizzes, so we will see that the percentages are quite different after the master degree. Okay, so now we can go to the second stage, so the PhD. So the first question that I will ask you now is what the percentage of female STEM PhD graduates, it refers to Italy in 2019. All the data that I collected are from Italy. Okay, so you can scan this QR code again. It's just for STEM again, and in Italy, as I said. So, okay, I give you just a little bit of time to scan the QR code and to answer the question.
So this is the master degree.
This is for PhD. PhD students, in particular PhD graduates. Quite
sorry, this is irrelevant, but I think your mic is off. We can hear you fine, but I don't think it's.
And you are right. I think the battery is dead, so I can continue without it. I have quite loud voice, so it's fine.
You can use the.
It's fine. We can. Okay.
Okay, so for example, Valentina, what do you think is the right answer for PhD?
I see very few female PhD students in general, so I think 35.
Okay, Valeria?
42.
42. You remember?
I remember
Okay,
the answer.
Okay. So the answer is 42. So it's quite higher than what you expected. So in PhD we still are good, so we're represented. And indeed, we can see this evolution, okay, from the bachelor to master to PhD, basically. So you see that the red line corresponds to female percentages, okay? So you see that basically it increases a bit and then it reaches like steady state, the saturation, okay? And for male, of course, in the opposite, because it has to sum to 100%. So basically this phenomenon, I studied, this phenomenon is called the reverse leaky pipeline. So basically there is, okay, an increment in the percentage of women till master students, and then it's average for PhD. To comment it, I would like to go a little bit through the other percentage because it's quite interesting that if we see not only STEM but all PhD percentages, we see that basically for bachelor and master students we have higher global percentages. In particular, you see here we are around the 36%, as we said before, but in general, as we said before, women are more inclined to go to university. Then we have more women in the bachelor than male in general for all faculties, for all courses. And this is also confirmed for master students. So actually, if we look at the general percentages, we are well represented at university. But if we go to the PhD, basically the percentages for male and female are the same. So like 48 to 52%. Okay. So the statistics for our programs are quite different. So I don't know if you want to comment on it or if we just go on.
No, I didn't notice what was the result in our score here in the room. So people found the correct answer or not?
No, people found that the percentages was low.
Low. Yeah. So this is, I don't know, it is interesting because, okay, this means the year is 2019, right?
Yes, 2019.
Now, the question is, when we answer these questions, what we say, apart from maybe a few people that really know the data, this is something that we think, and it comes from the media, I don't know, newspaper, the social networks, something. So it's very interesting how we are, even if we are scientific people, you look at the data only when you are very interested into some topic. And for me, mathematician, I realize that very often in life, I don't use mathematics when I make a choice. And it is stupid. I could do, and I could do maybe a better choice. So I think that this is also part of the problem, that we follow maybe some ideology or some mainstream, something, without collecting the data and having the, let's say, deep information about that. This influences us.
I was surprised that I thought also that the percentage was lower than this. Yeah.
Can I comment? I think that we have a bias as mathematicians because the STEM actually comprises also biological studies. So, you know, this very high percentage is related to the fact there is biology. Because I was the only one here reading in mathematics during my PhD year. So, you know, I mean, we are biased by that. I mean, in mathematics, there are no such good percentage of women taking a PhD, I think. At least in SISSA. I don't have the data for university, right? I mean, but in SISSA was during my years was not a good percentage.
For my year PhD, we are into me and Elisa, if I remember well. So yeah, 2 over. Well, I don't know, maybe 16, 15.
Maybe 4, because there was Maria Teresa and Valentina in the.
Right. You are right. Because we are the 2 applied ones. So. Okay, yes. I was wrong because we are the only.
The proportion is the same.
Yeah, but still.
No, if we're biased by that, I assume that we were like much lower than expected, also because I see very few women here as students.
Okay, so I think we can go after the PhD. So I just grouped here all the categories. I found this data for the percentages of women in all courses, so not STEM, but all courses in Italy in 2022. I found this for all the positions basically, so in postdocs, but I found also for permanent researchers. I think that this category is now no more accessible because it was before the Gemini tree. But now we have non-permanent researchers in Italy, so called RTD, and then associate professors, full professors, and finally directors. And then we will also compare these percentages with the SISSA ones. I found the data for SISSA, so it's STEM because we have neuroscience, physics, mathematics for 2022, so for the same year. So I will ask, it's quite a different type of quiz than before. It's I mean, still very, very similar, but maybe you will have to just write your name. It can be also fantasy name. It's not, it's still anonymous. Okay, not still anonymous. But okay, I don't know actually for this. Okay, maybe just go here. So what are the percentages for female? I will ask you just for associate professors, full professors, and directors. This is for all university types, so not STEM. So as you see here, the first is for associate, the second one is for full, and the third one is for directors. So these are the choices. So maybe this one, Maria, I didn't tell you. So what do you think can be the right answer?
I just say the first one because I'm quite pessimistic about directors. But it's also probable the last one, 25 ordinary professors, looks quite in line. So now I voted the first one, okay. But now I say the last one.
Can you change your mind?
Yes.
So Valeria, Valentina,
Yes, I also vote for the last one. It seems realistic.
Okay, let's say the first one.
Okay, here are the results. So you more or less all of you were on the same line. So the last one was right one. So you see basically totally decreasing percentage. And these are the data for the academic gender gap. So as I said, this is from students, so enrolled students, graduates, PhD, postdocs, and every non-permanent and permanent position till director. So basically, you see a scissor plot, like a scissor diagram. So here you see that from, I mean, the decreasing happens from the non-permanent position till the director, of course, directors. I don't know how many directors even, but for me, it's also. And it is for all positions, for all faculties or university types, not only STEM.
Look at the percentage when permanent researcher was there as a position.
It's still like 50%.
It was 50%.
It is because it's the data are from 2022, so still there are these positions, but not anymore accessible for applying.
Yes.
So maybe it was also like the Gemini law that called with this gap.
Yes, indeed. So in the 90s, when I won a researcher position, there was this permanent research position, and we were half and a half. I confirmed this, and I think that this was now disadvantaged very much with the cancellation of this position. So I said before, I think that females are very much scared by the future, no? With now, with these different systems.
Valeria, you want to add something?
I agree with them. Yeah, I think that the fact that you do not know when your position will become stable, something really frightening.
I mean, it's my opinion is frightening for both women and men, of course. But for women, maybe, as Maria said, there is also social pressure and other, say, elements that contribute to not continue career. Okay, if we go to okay, now I would like to do this after this data. Okay, if we go to the SISSA percentage, so the quiz now is what are the percentages of women researcher? It's global from RTD on, so from non-permanent researchers to full professors. Okay, at SISSA in 2022. So Maria already know the answer, so Maria no. Valeria, Valentina, what do you think is the right answer?
Researchers.
It's the same of before, but in SISSA. And for all the positions from
Professors also.
yes, from non-permanent researchers to associate full professors.
Let's say 29.
Okay.
So since there is also neuroscience, no, involved here, I would say 30, 35, maybe second.
I don't know from the audience if you already answered the quiz. Okay, very fast. No. Ah, and actually the right answer was 16. It's interesting to see that no one was right for this quiz. So this is a percentage, actually is, I would say, more or less in line with the national percentage because it includes all the positions, but it's quite low. Okay, I don't know about potato. Was the comment? But okay, here you see how the percentage vary during the years from 2015 to 2022. It is the actually not the percentage, but the number of people. So we have 15 female. These are new data, so I collected from your 15 female and 79 men. So this is just to have like a comparison also in STEM because before we saw like the general percentages. But for what concerns SISSA, so as we said before, there are of course like there is a very small number of PhDs, but you can see it's also from full professors and associate professors, at least in the mathematics area, it's very small representation. So if you want to add something, but more or less we already commented on it.
Just a question. These numbers include PhD students?
No.
No, okay.
No, it would be,
No,
I mean,
no,
it would be 15
yeah, that's
female PhD students.
So definitely in this room.
No, it's just from RTD, so non-permanent to full profession. Okay, so I have to come back here. So as we can see, there is this phenomenon that is called glass ceiling. So basically, women encounter like ceiling obstacles that in some way do not facilitate the advancing in the academic career. So now to the speakers, I would like to ask what is the reason that encouraged reasons that encouraged you to continue your career, or that will maybe encourage you in the continuation of your career? So this is the next question. I don't know who wants to start.
Okay, maybe I can start. No, I like this job. I think that this is what actually.
You're good at it.
I mean, I will let other people judge, but no, I'm not encouraged by the fact that I have good results. This is not something that I really, okay, maybe I underestimate me. This is also something that is really related to usually very sensitive people, you know, not be confident about their work. So I totally like fall in the imposter syndrome. This is totally. But I really like this job. I think that this is something that does not depend on your gender or in what you recognize.
So passion.
Yes.
What drives you?
Yes. Every day. This is the only reason. It's a very difficult job and it's not so rewarding in terms of, you know. Yes. I mean, if I would like to have a lot of money, I would not in academia, right? I mean, I'm not in academia because I like doing what I do.
Okay.
That's it.
Valentina?
Yes, so I think that now as you showed this data on bachelor and master degree, no, the presence of women is almost 50%. So I think that the passion, mathematical passion in females is not missing. But as I said before, no, maybe females are mostly scared by the difficulties in the academic path. And also, yes, you talked about education, no, before. So I think that nowadays there is not a big difference in the children education in the schools and so on. But maybe, so there is a scare of competition, which is was also confirmed to me by Massimo Gobino, who is the national responsible for math competitions in Italy for the Olympiads. And he told me that that girls wanted to take part to team in mathematics, to the team competitions, also individual competitions are very few, because they don't feel comfortable enough where they are under a strong pressure, a strong competition. And so some years again, the female team competition were introduced, and Massimo Gobino was not very satisfied with this, because he said, okay, but so we are now distinguishing again. Now we're going back with this new yes. But so he did this experiment nevertheless, and the result was unexpected to him, because there were many girls who did participate to this competition, which was reserved for girls, because they felt very much comfortable, they felt very much free. And he told me that there is some difference between the environment, the atmosphere which is created in men's teams and in women. So he told me that it seems that the women teams are much more collaborative, they are more friendly, they don't feel so much the need to demonstrate that they are better than others. So maybe in this sense, the culture is and education is also making the difference. So, for instance, no, so you in the high school already know you can see this difference in sports, or maybe also in music. No, usually the male teams are much more competitive and also aggressive, maybe, and in the women's side is not like this. And then I would say that so I think that it should be important also to encourage females during the bachelor and master degree And so it would be, since there are many girls and they are very good, it would be very important to encourage to be positive in this sense. And so, as we said before, it's important also to have some example of some women who succeeded to have an academic career and so on. But also male tutors and mentors, are very important, because I think that it's also very, very important when you have a male advisor who supports you, who believes in you, and who encourages you. So there should be done some education in this sense, which should be transversal, starting maybe from the high school and university years.
I like very much what you said, Valentina, because it reminded me the life of Mariam Mizakami. I watched a movie about her life, and precisely what happened to her, that she was in Iran. Clearly, there is a gender segregation much stronger than here. So students are separated. And this was, in some sense, a good point for her, because this was, let's say, helping her with her friends to train in order to participate to the Olympic Games in mathematics. It was exactly what you said about the experiment with Massimo Bobino. And somebody is telling me, okay, just think about playing basketball with Black people or white people. Sometimes there is the same, let's say, attitude to when you are involved in against the best people that you expect are the best. So sometimes your reaction is not that the right one. If you want, not in favor of taking part in the competition. I have another thing to say about this competition and cooperation. I had the experience to graduate here in SISSA with Gianni Dalmaso, and when he got, we celebrated his 60th anniversary, the speech he was saying, I prefer sharing to competition. And that was really the essence of the fact that it was a very, very stimulating experience to work with him, because he was able to create, let's say, collaborative atmosphere among the students. And this was, for me, very helpful, because I am not competitive at all by character. And the third topic is education. For sure, I don't believe that male are competitive and women are not. I don't believe that this is in biology. I think that this is more in culture. But of course, this is a big question for scientists. And the interplay between culture and biology evolves a long time. It's a question that should be studied, I think.
It's interesting. All the hints that you gave are interesting, and so maybe answering to the second question, what as an obstacle to continue the academic career, there can be also the non-competitiveness in a way of female. I remember that we did like an escape room in my group, and there were the non-competitive, competitive, and the non-competitive was only made of female, and the competitive group was only made of male. So it is, of course, it's not always true, but it can be a reason. But for example, Valentina, what if you want to answer, what is the main reason that is driving you now to continue your career, or that drove you before to continue your academic career? But you had passion.
Yes. So I also had a big passion, starting from the kindergarten. So I was really focused on this. I really loved mathematics, and I had I encountered many difficulties, but these were like challenging difficulties for me, you know. So I have such a character that I want. It is interesting to me to find a way to skip difficulties or to find a way to go through the difficulties. But and also, yes, I think the mathematics is really, so in general, no, we are very lucky to do mathematics because it is like another universe when we can go whenever we want, and it is very, very, very rich universe, and also can be very useful in the life because you always have this, yes, like an escape room, no? So you can go there, and of course in the life you have also other issues. You have family, you have relatives, friends, and so on. But I like to see this mathematics is like a friend. It's always there and will be always present. And so this was very, very motivating for me to go through.
Valeria?
I must say that I didn't have to fight because I was lucky. I am very old, and at the time, the position for researcher was essentially permanent position, because after 3 years you are evaluated. If you didn't do nothing, then you did something, then you remain in this position. But also maybe I was lucky because there were many positions. I had a wonderful opportunity here at SISSA to learn. So the difficulties were more on the personal side. So to fight more against me than against the others. So I'm not good enough. People are doing much better than me, and so and so. And to overcome this, I don't know, this problem of facing the difficulty to be good enough, at a certain moment, if you want, disappeared, because I understood that I like my job. This is a wonderful job. We have the freedom to choose what you want to study. We can travel. We can have a lot of social interactions because research can be done together, teaching is done together. So at a certain moment in my life, I was lucky also because I could have babies, I could have a family. So this is also an issue to have, maybe to find a job. You find a job in a place and your maybe family is far away. This is maybe a problem. So passion, I would say, and the fact that at a certain moment the difficulties are always coming. But okay, look at the good things. Look at the things that you like, and think that always there are people better than you, people lower maybe. Okay, if you enjoy your job, then nothing can stop your career.
And actually, another question came to my mind now. We saw the percentage, maybe we were discussing also before, we saw the percentages for Italy. And do you think that maybe the fact that these percentages are decreasing are also due to the fact that some women are moving to other countries to continue their academic career, but in other countries? Maybe it's the reason, or maybe it's because they just want to go to, I don't know, industry or other, not academic career. Because maybe the situation in Europe can be quite different. I focus on Italy, but maybe when I was collecting data, I noticed that, for example, for directors, but it was not even in academic field, it was in all fields. So, okay, directors, managers are 50% women, or even higher, for example, in Netherlands. And so maybe it can happen that just decide to go abroad. And that's the reason why.
I actually don't believe that in other parts of Europe they are better than us. They are very, if you think about also like Northern Europe, they have, I think, very low percentage of women in academia. What happened in the Netherlands was actually straight policies of recruitment of women. This is the truth. Yes. The Netherlands is like one of the the countries that said, okay, now we have to stop this kind of issue that we have, and the only way we can solve this problem in a fast way, so not relying on education, not relying on culture, is like, okay, now we have to hire women. Now this is quite a hot topic, because Quote Rosa is always, I don't know how to say in English. What's the name in English?
Controversial.
I heard controversial. No, Quote Rosa. No, we don't have an expression for. Okay. So Quote Rosa is when basically you decide that a percentage is reserved to women. Yes, and now I have like a lot of mixed feelings about Quote Rosa. So I don't know if I have to start. Maybe I can hear what you think about Quote Rosa.
Yes, this is difficult to reply. So I think that we should increase in any case the percentage in some sense, but of course, in scientific, in the academy, you have to choose the best candidates. No, so we should maybe encourage females to take part competitions and to make applications, and maybe to give some substantial advantage to university who decide to hire females. And also, I think that maybe we should increase the number of grants and yes, maybe the PhD grants, could be dedicated, a part of them could be dedicated to females in order to encourage. Then when in the university research institutes, of course, you must choose the best one. When we have two candidates which are completely equal evaluation, yes, it would be preferable, as ICPT does. No, so I think that UNESCO in general does this. And in parity condition, you are the committee has to choose a women candidate. Otherwise, I think that it is not correct to just a priori decide to reserve some position to women. But this is also true that we have to absolutely we have to improve this percentage.
Yes, I have 3 babies, a girl, a boy, and a transgender. So my position towards gender is very, I try to be balanced, because I do not want to favor anybody. So I want to favor everybody. So this is a very difficult topic. From another point of view, if you look at how the position of women in society in our world, let's say Western world, changed during 1 century after two world war, you see that women didn't vote, women didn't work, women didn't have any position, and we do not want to wait for another war to improve the position of anybody, any minority or majority which is excluded, who is excluded from something. So any attempt to improve this could be tried at least. And now we do not use anymore this pink name, let's say Quote Rosa, but there are these, for example, fellowships for the gender which is less represented in a certain field. So, because if you want to balance, it means that somebody in some, let's say, area you should increase, and in some other you should decrease in principle. And finally, I don't know if there is an a priori what is better. That, for example, you see now medical doctors are more and more women. And why, and is it better? It is very difficult. So I think that to look at this problem, we cannot just discuss, okay, we can share our ideas, but they are very deep. And so I cannot say what is the answer.
It's interesting because I mean, Poderosa is a very hot topic. It's difficult also to say, okay, let's do it, or maybe enforcing is not the right way to do. But yeah, I think that, but you can comment also. I think that maybe another issue is that, for example, in PhD programs, women don't even apply for a position. So I think also at SISSA we had these problems also when professors had to decide there are no women that apply, so it can be an issue. So maybe this obstacle we are talking about maybe is even before. So as we said before, we should maybe somehow act in an earlier age. So, for example, in high school and secondary school. So, what do you think? You think that it can be maybe we should act before? We should act before on female or on male. The reasoning and thinking, prejudice.
I mean, the problem is for sure before, like, you're right, people are, I mean, actually, people are not applying for positions. And then, I mean, it's related to what discouraging, right?
Yes, yes.
So, in my personal, like, I mean, I can only share with you my personal life. I still think that I do not belong to this place. Like, it's a very deep feeling that I have. And people that know me, I mean, they know that I'm quite extrovert, quite funny in my normal life. But when I have to work, and even when I work with people that I like, my friends, if there is, I don't know, like a Zoom meeting, and I realize that, and if there is a Zoom meeting with a number of men that is greater than one, and there is no woman with me, I feel the pressure. Like, I always stay silent until they finish talking. And they start talking on each other, you know? And I realized that I do that, and I don't know why. Like, I'm usually one that speaks over people in their life, you know, very loud. But while I'm working, I feel somehow I'm scared of sharing my opinion, you know, even if they are, maybe they can be right or they can be wrong as the other colleagues' opinion, right? So I always had this feeling of not belonging, of not being in the right place, not being, yes, like good enough for my job. And I still have it. I mean, I'm trying to work on it. But it's really difficult because we are very few women. I mean, now I'm starting to lose control of all the things that I have to do for my job. So I have a list with names, usually, like, you have to do this for this guy, this guy, this guy, this guy, this guy, and they are all male people. Only when I work with Anna, I have Anna, you know, and I write that name. So every time I'm there, I mean, I suffer so seeing this stuff. You know, it's really complicated for me. So yes. And for us, it's really complicated too, not having like a community, a female community, like that can deeply understand you in what are your past experiences as, you know, a woman or whatever. And then this is, of course, enlarged to any kind of less represented community, right? So yes, it's challenging for me. And once again, so yes, this is the answer to the second question. And of course, we have to build up something from a cultural viewpoint, for sure. I mean, I think that the reason I am like that is because somehow the culture told me that I was not good enough, or as a woman, I should be, I don't know, silent and think twice about what my opinion is. Okay, I don't know.
Maybe as we said before, also having like a female mentor, a female supervisor can encourage you more, of course.
It's not the supervisor, I mean, it's about community. Like, I feel really comfortable working with you, working with another colleague of mine that is female, because we have the same way to interact. I usually feel comfortable one-to-one, female-male, okay? And I think that is strongly related with my the relationship that I have with my brother. I have an elder brother. So I think that is strongly related to that, but I do not feel comfortable in a room with two men talking about mathematics. Already 2 men is too much. One at a time. One at a time, yes. I mean, it's to be fair, like it's something that
maybe it's also something personal.
Yes. I mean, no, it's totally. But I mean, I know that it's a problem of mine, but of course it's cultural, you know. Because if I go out with you, I don't think that you will say I'm not comfortable enough with, I don't know, other people in general. So it's job related.
So also, I have just used like a question, and you can comment on it and say what you want. Okay, so maybe as we said, mentorship is important, but collaborators, having collaborators. But I would say I would ask you, is also like family important? So, for example, I grew up in a family of professors in secondary school, so I was quite lucky. I mean, they were encouraging me in doing university, not the same way into the PhD, and even they are professors. So I mean, I would not imagine, for example, other families. So is this, for example, the thing that influence also the choice of this?
Yes, sure. Surely the family influences very much the choices. But I had a family who was against doing PhD and whatever. So, okay, it is possible to do this also against the family. But I think that, yes, one problem is, as Marta said, self-confidence, lack of self-confidence. And I had this at the beginning of my career, and it took about 20 years to come over this. But now I feel comfortable everywhere. But this starts from the family, no? Indeed, in my family, my parents used to say, "But no, why do you want to insist by this? This is not for you. You're not good enough." And the other thing, I also see this organization like in Italy for families. So, but this SISSA is particular. No, you have the kindergarten here you have many opportunities. You can take some leave for staying with the children and so on. So I think that maybe in the course, for instance, SISSA could emphasize this aspect, and girls should be encouraged by showing that there is possible to organize the life in order to have both work and family.
I don't know what to add because they said all more or less. I may just say that our school system is, even if in the constitution, in the law, the main law of the state, it is written that everybody should have the same opportunities. Our school system is still not enough to help people to grow up in the social level, and this is valid for everybody, in particular for women. So the influence of the family in the sense of your social origin is something that counts.
Thank you. So if there are questions in other topics that you want to touch, you can just raise your hand. Guys, okay. I would like, this is the past, okay. Okay, I would like just to conclude this panel discussion with a fancy website that I found. It's on the Gender Equality Index, so it's a website where you can find some data, so index, or in general. It's difficult to interpret these indices, but are related to the gender equality in different fields, so like economics, the payments or the stipend of women, men, and so on. And so it's interesting because in the home of this, in the home page of this website, you can like choose your perspective. So what does your life look like as a woman from Italy? And actually the website returns these boxes. So here, for example, it says in your national parliament, the 36% of decision makers are women. You have the 17% of chance of graduating from university, while 14% for men, but this is related to what we saw in the initial part of this panel. So women are more inclined to go to university. At work, women earn 43% less than men. And then finally, you are 38 percentage points more likely to go out of work. So it's just a very, very general, so it's not academic, so it's general panoramic of, let's say, what's like being a woman in Italy. But it's just to conclude this panel. I would like to thank you all for being here. It was quite interesting, also for me, giving your opinion. And now we can go for break. Okay, so we can start with the seminar. Seminars, so with the scientific talks, and the first speaker is Professor Valentina Beorchia from the Department of Mathematics, Computer Science, and Geosciences in Trieste, so the University in Trieste. And she will talk about the geometric approach to tensor eigenvectors. So the stage is yours.
Okay, so thank you very much for having invited me. Thank you very much to Anna for this nice opportunity. So I would like very briefly to show some topic from my research, and this will be non-technical because I know that many of you are not experts in algebraic geometry. So I would like just to give you some pills of these possible topics. And I try to be as much computational as I could, because maybe when you can see application and computations, maybe this is, for many people, this is more comfortable. I would like to say that algebraic geometry is a very classical topic at the Italian algebraic school. Algebraic geometry school was very strong already in the beginning of the 2 centuries ago, and it has been for a long time considered, yes, very classical and a little bit obsolete, topic. But then in the last 20 years, there was a huge explosion of these techniques, because there are many applications in multilinear algebra, and so in particular in data science, in physics, in other fields. So for instance, in Leipzig, there is the Max Planck Institute, which has a very strong section working on this. There is Professor Bernd Stuffes, who is one of the directors. And so the last SIAM meeting, which was last year in August in Eindhoven in Poland, it was just an application of algebraic geometry to tensor problems, to cryptography and other topics. So there were 17 parallel sessions and about 1,050 participants. So I would like a little bit to show this. So, sorry, I'm not able. So maybe I use the old way, no, but I can use these arrows.
Okay.
Okay.
Should work.
Okay. Okay, so we just start giving the definition. So here the idea is that generalize eigenvectors of matrices to tensors. Okay, there are many ways, but this is one which is suitable to various frameworks. Okay, you will see why. So we start just with a tensor of order D, which we choose of this type. Okay, so in B-dual, so B is a vector space of finite dimension. Let's work over the complex number, but many of the things you can do also in the real, also on other fields, on finite fields. Just to simplify, you take the complex, you take a tensor of this type, so that you can evaluate this contraction. You take a non-zero vector, and you can consider the self-product, tensor product of this vector by himself, and you say that B is an eigenvector if you have an identity of this type. When you have a square matrix, you have this, D is just equal to 2, and this is one possible relation to of eigenvector of a square matrix. Okay, so let's do some comments. Okay, so you can, if you fix some non-degenerate linear form of V, you can identify the dual of V with V itself, so that whenever you have any tensor in a tensor product of V times, you can, by this identification, you can give this definition, and also you can write down this definition in coordinates, of course. So for instance, when you are just in the standard vector space of dimension n+1, a basis is given by all these expressions, where, for instance, where the E, I, J are elements of some basis of Cn plus 1. Of course, it is standard to just to choose the standard basis, the canonical basis, and with this you can write down some coordinates of the tensor. So here you can say see it indeed as a higher order matrix where all the entries, the coordinates depend not only on 2 indices, but you have in general the indices, and this picture is typical when we do promotion of this topic, because you have so order 3 tensors you can imagine as a cube, no? Or if you want, in this case, three matrices, one behind the other. So there are many contexts in which this notion appears. Here you can see a list of this. Very recently, I discovered that there is a group in SISSA working on tensor networks, and I'm not sure if they are connected in mathematics or with physics, but it would. So I will try to have some contact with this group because I am really interested in see if we can collaborate. Okay, so for instance, just to understand what we are doing. So when we do this contraction, so now if we work just in coordinates, you take, for instance, an order 3 tensor. So you can organize the coordinates in a box, in a three-dimensional box. And you can imagine this like n plus 1 matrices, one behind the other. And doing this type of contraction means that you are making a choice of some direction. So you are consider this box, you consider some slices. For instance, you did the first, if you fix K, the third index, and you let vary the first two indices, this determines some matrix, and which is called, in this case, the frontal slice of the tensor. So in general, this definition depends on the slices that you choose. If the tensor is symmetric, meaning that whenever you permute the three indices, you find always the same entry. It doesn't matter which direction you choose. Okay, so sorry. Yes, so you write this contraction, the case coordinate of this. So this is a vector. The case coordinate is given by this sum. So, to be very concrete, you take the case slice and you apply to the vector on the two sides. And also here you can see that you have some polynomial. This is a quadratic polynomial in the coordinates of the vector v. And it is also, we can see, it is a homogeneous polynomial. Okay. So what happens? It happens that this expression, so the case coordinate, does not depend really on these coordinates, no? But whenever you take some tensor whose form, when you restrict to some slice, you find some quadratic form. So this now is a symmetric expression. So if you take a tensor, and I don't want to give details, but you partially symmetrize, meaning that you fix the slices and then you do the symmetrization of these slices, you find the same output. So, okay. Yes. So here we have some remarks. So this notion of eigenvector is a homogeneous notion, meaning that if you have some eigenvector, you multiply by a scalar. So this multiplied vector is again an eigenvector, but the proportionality. So what we could call the eigenvalue is not the same as before, because this is now multiplied by v, but now here the scalar has changed. So here we don't have the notion of eigenspaces and so on, but nevertheless the definition is homogeneous. Okay. And also here we have another remark. So whenever you take a symmetric tensor, for instance, in the real case, but also in the complex, so you write, whenever you have a symmetric tensor, you can associate a homogeneous polynomial to this tensor. This is like for symmetric matrices, you associate a quadratic polynomial, the quadratic form. So you have this polynomial, and computing this contraction corresponds in doing the gradient Okay, so here the slices of the symmetric tensor can be seen as the matrices, the tensors which are associated with the partial derivative of this polynomial. So like for symmetric matrices, you can see the columns of the matrix as vectors which are proportional to the gradient of the quadratic map. This happens for the same thing. So here, not in the real case, so you can give an interpretation of this definition in terms of functions. So you have that in this case, a vector is an eigenvector if and only if you have this equality. But then this you can interpret as a critical point search, no? Because so this is the gradient of f with something which is proportional to the gradient, evaluated in V. And what is the vector V? The vector V can be seen also as a vector which is proportional to the gradient of the implicit equation of the sphere in R and amplitude. Okay, so if you use the technique of Lagrange multipliers, you see that this holds if and only if when you consider this polynomial function, homogeneous polynomial function, you restrict to the unit. Here, so sorry, there is Sn, there is a typo. With values in R, you're looking for critical values of this. So this notion has been for the first time detected in a paper in astrophysics of a Russian two Russian astrophysicists. And because this function homogeneous polynomials restricted to spheres are used for the approximation of some gravitational fields, which I'm not an expert, but this is why also this notion is quite natural to be considered. Okay, so as I said you roughly before, you can also you take any tensor and then you fix some direction. You fix these slices and you do the symmetrization of these slices. So each slice now, which is symmetric, corresponds to some homogeneous polynomial of degree b minus 1. So you can represent a partial symmetric. These are called partial symmetric tensors. And you can represent it by n plus 1 homogeneous polynomials. So here you write in this way, in the partially symmetric case and symmetric case, the definition of being an eigenvector. And again, these are a homogeneous equation, meaning that this hold if and only if they hold for any scalar multiple of the vector. So it is very natural to restrict to some unit sphere, since they are homogeneous, or for in algebraic geometry is more common to restrict to projectives, to the projective space. No? So you look at this equation in a projective n space that's over C, but also on any other field. You can do this. So you can express this condition of being proportional. So you want these n plus 1 components to be proportional to the n plus 1 components of the vector. But we don't care about this scalar. Okay? This scalar in many environments is not important. So how do we express the fact of being proportional to the vectors? A natural way is to take the matrix 2 by n plus 1, and you posit this matrix has rank 1. Okay? Also because in general, it is difficult to find exactly eigenvectors. But here you see, with this expression, we have equations for all the possible eigenvectors. So with this expression, we get all of them. No, we get the equations which are precisely characterizing this. So this in algebraic geometry is called a scheme, because this can be also very, very odd, can have some So the zero locus of these minors, 2 by 2 minors, can be also of mixed dimension, can be some components of dimension 1 or more, and other components of dimension 0. You can have also multiple components. So this is called an eigenscheme. And it is in a particular a determinantal scheme because it is defined by some minors of a suitable matrix. So here you have this toy example, which is very famous. You take the Fermat cubic, which is these homogeneous polynomials, x1 cubed plus x2 cubed, x3 cubed. So you have a tensor, symmetric tensor, which is associated with this. What are the entries of this? This is just the entry 1, 1, 1. You have an 1, 2, 2, 2. You have entry 1, 3, 3, 3, entry 1, and otherwise it's 0. Okay, and you write out the condition of being eigenvectors, and you find these equations, and you find exactly 7 eigenvectors up to proportionality. Or in the projective plane, there are these 7, and then you have this beautiful configuration in which you have 6 triples of a line we call eigenpoints. When we are in the projective, we call these eigenpoints. Okay, so it is possible to give the number of these eigenpoints in general. So if you take a general tensor, it has been proved in 2017 and then again in 2020 that if you take a partially symmetric tensor which is general, what does this general mean? It means that you have to choose it out from some hypersurface surface, which is called the eigendiscriminant. So as usual, you can collect all the objects which have some odd behavior. So for instance, not having pure dimension 0 or having some multiple components, they form a hypersurface, and the degree of this has been computed. So if you take some tensor out from this hypersurface, you have that in the projective plane, this is reduced 0-dimensional. So if you want again to do the analogy with matrices, if you take a general, let's say symmetric matrix, this is in general, this is diagonal, this can be diagonalized. And in general, the 3 eigenvectors are linearly independent. No? You have the 3 eigenspaces which are linearly independent. No? You have for in spatial cases like, I don't know, an eigenspace of dimension 2, an eigenspace of dimension 1. No, necessary sufficient condition is the characteristic polynomial has some multiple roots, and this is a special condition. So in general, this is 0-dimensional, meaning that in the vector space you have these vector lines which are independent one from each other, and the length, meaning the degree. So these are points in projective space, and how many of them, this is the number. So here this is the order of the tensor, and n+1 was the dimension of the vector space. So as I told you before, the first time that this number appeared, it was for n equal to 2. And it was given by these 2 astrophysicists, Kuznetsov and Kolchennikov, in 1992. But there are also people working in complex dynamical systems found the same number, and then it was reproved in 2013. Okay, so this was just the introduction. So now I really have, so in this direction, we had a number of results concerning the geometry of these configurations, and also concerning all the equations of subsets and so on. So this now is going to be technical. So I just show you, just to show you how it is incredible that we can use very classical techniques, both from algebraic geometry and also from commutative algebra, to find then information which are which are interesting in this context, because the geometry, so of this configuration, so for instance, in the order 3 case, you have 7 points in general, for D equal to 3, and N equal to 2, this number is 7. So for the Fermat cubic, we had 7 points, and we have in general always 7 points. And for instance, to see if there are some collinearities of points, this can be then used to give us information of the tensor. And now in this context, the standard classical techniques can be used very efficiently. Okay, and so for instance, so this is what is called the minimal free resolution of this idea. Is there anybody who is familiar with commutative algebra? No. It's a while ago, but you can see exactly the degree of all the equations of this, and then all this, what are called the syzygies, the relations between the generators and so on. Okay, so then the questions in this context, and what type of configuration can you find if you can construct some algorithm to check if some points, if a correct number of points is the set of eigenpoints of some tensor, of some symmetric tensor or not. And then you ask the same questions in higher dimensions. So we gave answers to all of this. So a first one was given by Dogger, Siegel, Sturfels. And here you see that a triple of polynomials are the 2 by 2 minors of some defined matrix, if and only if you have a relation like this, where this and I are linear polynomials, and the 3 linear polynomials must be linearly independent. Okay, so we then gave with 2 students, Francesco Galuppi and Luca Venturello, we added this, so you can also detect when a triple polynomials are the minors of a defined matrix of a symmetric tensor. So we have also this differential equation, which must be satisfied. And this is also classical. We use just the RAM sequence on the affine space, and we find this. Then you can, from this, you can build an algorithm, so you can test if some points are the eigenpoints or eigenvectors of some tensor. And just looking at the idea, so this idea is given by the set of all equations of all polynomials vanishing on this set. And then you have many symbolic programs who give you all the relation among these, and you look at the matrix that you get, the matrix of relations, and you can use the result of the algorithm. Okay, for the symmetric case, again, you do this, and you have this one. And then there is also a geometrical equalization. So in the case just of order 3 tensors, you take 7 distinct points in the projective plane, and you wonder, you want to understand when these 7 points are eigenpoints of some tensor. So the first result was very simple. So this is an eigenscheme, even if you, whenever you extract 6 points, they don't lie on a conic. So if you remember, 5 points are always on a conic, and 6 points can be or not. No? So this is a geometric condition, and so we characterize this to any for eigenpoints in the plane in any degree. So you have no D+1 collinear points, and you will never have KD points on a degree K curve. So for instance, here you have 2 by 3 points, no 2 by 3 points on a conic, which is a curve of degree 2. So it is possible both to characterize by equations and by the geometry. Then also it is possible to count the maximum number of collinearities. So for in the degree 3 case, you never have 4 aligned points, but you can have 3. But the number of these is bounded, the number of triples is bounded by this number. And it was very funny because to find this, we constructed a suitable ramified covering of P2. And this comes from the degree, so for people used to covering theory, this comes from the degree of the ramification. And whenever you have an aligned triple, this line is contracted by some suitable covering method, and so you have at most this number. Okay, it's possible also then 2 years later, we generalized this to high dimension, and we had relations which are very, very similar to the dimension 2 case, and also for the symmetric tensor, we have this differential relations. So again, you can use all this algebraic stuff to construct some algorithms, so you can construct a test for some forms, homogeneous forms, to detect whether they are 2 by 2 minors of a matrix of a suitable time. And also you can test if some points are eigenpoints. So if some people then is interested in these lines, I can send it to you. And also in the higher dimensional case, we have a beautiful geometric description of this loci, because so this matrix like this is the defining matrix of the set of eigenvectors you take, but now you don't have this matrix is 2 by n plus 4. So here you have to consider all 2 by 2 minors of this, and these are the equations. So whenever you cancel one column of this, you find something which is now a curve, okay? And similarly, you can delete 2 columns and you take 2 by 2 minors, and the zero locus turns out to be a surface. So we have this characterization. So some points are eigenpoints if and only if there are the intersection of 2 curves of these types of one surface. Okay, I think that okay, I will finish. Okay, so these things about the eigenvectors is important in optimization. Also, when you want to approximate some tensor with a lower rank tensor. And the special geometry has already been used in some context to have some important information. Okay, so now we are studying the locus when we have at least one triple of aligned eigenpoints. And so I stop with this. Thank you.
Okay, thank you, Professor, for the nice talk. So are there any questions, curiosities from the audience?
But also, if you're interested, we can also discuss after. If anybody has some connection with his research, I would be glad to discuss.
Are there any questions also from the online audience?
Curiosity, but this is not 2 dimension. What was the tensor dimension, what the space dimension? You always
no, you have in general, you have always a 0 dimensional. Yes, like also for matrices, no? The matrix is 3 by 3. So the general one has the 3 eigenspaces, there are 3 lines, no? And when you go to project it, you have 3 points. But also n by n symmetric matrices, they have all the n, in general, the general one has n different eigenvalues. Because you look at the characteristic polynomial, and the general characteristic polynomial is this factor has n different linear factors. So also for matrices, the order of the matrix can be anything, but this locus is zero dimension.
Okay. Any other questions?
Maybe you mentioned that there are applications to cryptography. Can you just give us some generally because
But the no,
tensor algebra you meant?
the tensors not directly. The cryptography, so you have this algebraic cryptography. So you have the theory of elliptic curves when you have some group structure on the curve, and you use this to encode information, and then some generalization. This has been done for hyperelliptic curves. And you work with some other group structures. This tensor framework is used to encode the data. Then you can compress this, and then you can encrypt this. There are many ways to manipulate these things.
So let's thank again Professor Valentina. Time to restart. Just a moment. Okay. Now it should work. Okay, so I'm happy to have here also with us Professor Valeria Chiadò Piat from Politecnico di Torino, and she will talk about multiscale modeling of masonry structures.
Thanks a lot for this kind invitation. It's a pleasure to be at SISSA, because SISSA is like a home in this sense. Okay, the topic is something that I was working long ago, and recently some friends asked me to discuss together. So I realized that there have been a lot of improvements, and so I had to study a lot. But okay, so what I will tell you is more about the story of the problem than the results themselves, which are not completely ready. So this is a joint work in progress with Anderson, Melchor, Hernandez, and Morandotti. Anderson is coming from Colombia. He got the PhD in Pavia, had a postdoc in Politecnico di Torino, and now he's in Bologna. And Morandotti graduated here at SISSA, and he's professor at Politecnico di Torino. So, and there is a sponsor, the PIN project, and I have to say that this is also sponsor of the research. So these are the topics that I want to touch. So we will discuss a bit what are variational models for walls. Masonry structures means just in essence walls. Then my favorite topic that comes from the bachelor thesis, if you want, to use mathematics in order to obtain macroscopic models about something where you know microscopically what are the properties. And the work in progress is related to the case of walls. So this is the house. We bought this house in the countryside, and we have to repair it. And the walls are partially bricks, partially of stones, and there are a lot of problems. The paper that I consider my, let's say, reference point is that of Gabriele Anzellotti, 1985. Maybe he was one of the first persons who found a way to put the problem of static equilibrium for walls in terms of minimization of some energy. So the paper was interesting for me because the equilibrium of a wall expressed in terms of a system of PDEs could be also seen as a minimization of some energy functional with constraints. And this was an opportunity to, let's say, use this space BD, bounded deformation displacement fields, which was introduced just a few years before, in the 1980s. So just to pick some notation, assume that you have a body that occupies some domain, omega, and this is okay. And the displacement is u at x. It means the field such that x plus u at x is the position of the particle after the deformation. Suppose that you have some forces inside the body and at the boundary. And what is called the strain is the symmetrized gradient. So gradient of u plus the transpose of the gradient of u. So this is a symmetric matrix. While sigma will denote the stress of the symmetric matrix. So in that model, the tensors are stress tensors are negative semi-definite matrices. And this means that, in a sense, the body does not sustain tensile stresses. In the sense, it is easy to break while pulling, and instead it is very hard to, let's say, to destroy or to damage the wall by compression. So at each point, if you take a surface element S with a certain normal nu through the point X, what happens to the tension in the direction of the normal? It happens that it is directed against the surface and not out of the surface. And this means that the product F times nu is non-positive. So in the following, this K0 will be a subset of matrices, a column, let's say, of the matrices that are negative semi-definite. So the problem of what is the equilibrium? What is the equilibrium of a body where of this kind, where there are some forces, internal forces, and so on. And at the boundary, so here this is the equilibrium equation, balance on forces, and constitutive equations that tell us which kind of material are we dealing with. So these three conditions have the following interpretation. The first one, as we said, it means that the material is easy to break and difficult to compress. And the others say that the strain can be decoupled as a sum of a part which is proportional to the stress and the part which is orthogonal to the stress with some properties. And essentially, this lambda is normal vector to this convex cone K0, which means for the specific case some lack of cohesiveness. So what was the merit of this guy, of Angelotti, was to replace the system by, merit from my side, because I'm interested in functionals and minimization of energies. So to write the problem as a functional where the main term is, let's say, some integral that analyze, that count the energy coming from not the whole strain, but the part of the strain which is projected on the set K. And here we have just the work of done by the external forces. For which displacements U, for the displacements that are in some, let's say, set of constraints, which means that they have bounded deformation, and for which this integral is finite. So this was the proposal, and so this projection is computed with respect to certain tensor, so it's equivalent to the standard scalar product, and this name BD is the set of vector value and one functions for which this symmetrized gradient is a measure with finite total variation. So what was the result? At the time, it was well closeness of that minimization problem. So Angelotti proved that
he found suitable conditions for which the minimization of that functional in that set has a solution, at least one solution, and corresponding stress is uniquely determined by means of this projection. And it satisfies the Neumann problem expressed in terms of equations. So this was for me the starting point to look at the problem from the side of functions. So I will skip the technical details, but the classical method of calculus of variations were used. So he wanted just to find, let's say, the suitable space and suitable topology for which his functional was lower semi-continuous and coerced. So let's say to apply the Weierstrass theorem from the point of view of existence of meaning. So next, now we will go to the problem that I'm more interested in. So from a microscopic structure to macroscopic, and we will see that it is convenient sometimes to look at the strain as sum of several pieces. One piece is the part which is considered that the strain is vector valued measure, matrix valued measure. So a part which is absolutely continuous with respect to the bag measure, and the part which is singular. The first part, in a sense, represents a continuous deformation. You can maybe deform some elastic domain, some elastic material without breaking it. And the other part represents instead the possibility to create fractures. So they are very important, both of them. So for technical reasons, I will not discuss details. This singular part may have a part which is related to fractures and another part which is called the Cantor part that I imagine more related to damage. So I don't know if this is the correct interpretation of the mechanisms, but okay. So I will skip this detail. I just want to say that in the definition of the species, it is very important to identify what does it mean a fracture. If you imagine that the displacement means that now you have a point, and after a while, this point is in another place. What happens if your function u is not continuous? It means that if it is discontinuous, this point goes to two different places in a sense. So it means that you create a fracture. And this definition is, let's say, what are the sets, which are the points where you create fractures. These are points where this vector u has different one-sided limits. So for one side and from the other side, there are different limits. Okay. So this measure is concentrated exactly on the jump set. This measure, the singular part ej of u, and it can be expressed as, let's say, u plus minus u minus tensor product, symmetrized tensor product times the normal along a certain direction. Okay, we see this. This is a nice space, nice topology, and now we go to from micro to macro. So instead of looking at a wall as a homogeneous object, I look at the wall of my house that is made of stones or bricks, and I want to understand which properties of these stones and bricks bring let's say, the same model that Anzelotti recovered from far away, let's say, as if it was, let's say, homogeneous. So in the paper that now you don't read the title, but the title of this paper is Another Brick in the Wall. And it's a paper that it is impossible to find in the literature, because if you look on the web, you find, of course, the people. So, but it existed. It was 2006 together with Andrea Brides. And it was the attempt to find this functional as a limit of structures made of small bricks. So we were using, let's say, the tools of Gamma-convergence. I don't know, I guess this term is, okay, it's a notion of convergence that preserves the minimum value. Let's say like this. So we want to find that this macroscopic energy is the correct one coming from a microscopic model. So we describe the wall through function as f epsilon in this form. Let's say that now f epsilon is the same, let's say more or less integral, but on the set omega minus the boundary of the bricks. And along the bricks, along the boundary of the bricks, we prescribe, so we know the shape, and we prescribe that they cannot be pushed together, they can only be separated. So this is a constraint that says that the wall may break, in fact. Okay, so it's expressed in terms of a cone condition. So U plus minus y times the epsilon should stay in that cone when x is at the boundary of the small bricks. Epsilon is small. This structure is periodic, and we want to see what happens when epsilon goes to 0. So when I go far away from my wall. Okay, so I skip the details. These are examples, and we find, in fact, a limit problem well defined. Here in this slide, it's quite technical. We describe the integrand of the limit functional, which is expressed in terms of a minimization in the periodicity cell of our structure. And where this function is 0, this is a cone of the tensile stresses, which means that you pay no energy to break the wall, in a sense, by pulling. And this is instead the cone of compressive stresses. So what happens is that this enters into the description of our wall. So the theorem was like this: if we assume that only smooth deformation have a cost, and to break it pay nothing, then we prove that, let's say at the time, this f epsilon really were close to the model that was similar to that of Anzelotti by means of a certain, let's say, integrand, which was described by the previous one. So it's quite technical, but was a way to recover the macroscopic model of Anzelotti. And in computations, in simple examples, in 2D, we see that, for example, if we take the structure like the lattice, and we take to be K1, if, let's say, the detachment can take place only in this way, so this term should be proportional to the normal nu times a positive or non-negative constant, then we find that the formula that we get brings what is the possibility of, let's say, what are the zero energy displacements. They are really those that may allow the structure to break. And more recently, Brides worked on a nicer problem. So at the time, we were working with, let's say, just wall made of bricks that can be separated, but they didn't take care of the fact that two walls contain also some glue among the bricks. So we did recently this work with a mechanician, Dargi. So from this dry wall, the muria secco, we say in Italian, to let's say walls where there is some mortar joint among the bricks or the stones. And so they added, so the previous energy was the same. Now they added recently this term. Please tell me if I have time. Okay. Okay. So the interesting work they did is to add something that penalizes the fracture, the creation of fractures by this surface term, which let's say is positive if you have, in fact, some fracture in the set of jumps. They found also an additional surface term in the limit. So it means that their model, in fact, takes into account that in presence of mortar joints, it is not that easy to break the wall. It's not as with dry masonry structures. There is an explicit expression of this homogenized, and here what happens is it appears what is called the recession function, which is, let's say, the slope at infinity of the function. And the interesting feature is that this is non-trivial functional, having different growth from below and from above. And in explicit examples, they show that, in fact, these represent nicely materials that sustain, let's say, support some small, let's say, stresses also under tension, but it is convenient to break only for large stresses. And a completely different kind of study was performed in these years by Chiesi Dalmaso and Dalmaso Zeppieri, where they were working instead on a structure where, in a sense, the bricks are of bad quality. They can break. So the gray region is made of something that can produce fractures, but around these structures you have some nice material, elastic material. So these are, let's say, reinforced structures, and here you see just a cross section. So you imagine just pillars of, I don't know, mortar or not mortar, or come si dice, cemento, concrete, maybe, pillar of concrete, and around them some elastic material. So they studied this problem where there is a periodic array of these structures, and there is a parameter delta, which represents the proportion of the two materials. So now, in this case, this is a vector. Before we had a vector value function. Here, u is from R2 to R. This is scalar functions. It represents the antiplane shear in the sense that the material deforms in one direction. And from the mathematical point of view, still it is quite complex. They are able to prove their results only in this 2D setting. And they describe the behavior in different situations according to how big is the amount of elastic material, the white region, big or small. So they have three regimes in their case. So in the extreme cases, if this parameter is plus infinity, it means that you have a lot of elastic material, then you do not break. It is natural, and you have the result of this kind. You have a limit which is finite only on smooth functions. Otherwise, it is plus infinity. It's impossible to break the structure. Instead, if theta is 0, so in a sense there is a little amount of elastic material, they have a limit of this type where there is a contribution both of the bulk energy and of the surface. And so we are at our work. We are mixing the two models. That is our, let's say, work in progress. So we are working on a structure similar to that of Dalmaso, Chiesi, and Zeppieri, but we are working in a general dimension D. And instead of having, let's say, the gradient with u scalar value, here we have the strain u in full d-dimension case, and with the additions of the constraints as in the problem of Anzelotti. So we are mixing the two problems, if you want. And so I think I'm running out of time now, but the constraints are here. We prescribe where the fractures are allowed in the gray region and which kind of fracture we permit. Only fractures that respect the condition of the cone. Okay, and so there are some technical assumptions on the cone. And for the moment, we are working in the proofs of this result, which are not far from those of both the two communities, in the sense. So we expect to find, let's say, a general integral, a general energy function made of two terms, one which relates to the internal deformation, the other one relates to the production of fractures. And this is for the moment only when theta is finite, with an explicit formula similar to that of Brides and Mudargi for the integral f and for the set of constraints at the macroscopic level. So steps of the proof are standard, but we have a lot of technical details to solve. The literature behind the problems is here. So now we go to more recent papers. That one, Brides and Mudargi, was published in 2020. And to conclude, I want to say that our dry stone wall broke recently because of too heavy rain. So we have to study more mathematics for technical problems. So thank you.
Thank you, also Valeria Chiadò, and time for questions. So are there any questions from the audience, curiosities?
Thank you. I mean, it's a very naive question. Of course, I'm not an expert, but when you talk about microstructure, usually you think about the shape and then it repeats. So my question is about the shape. So how it does influence the convergence.
It's very important.
Okay.
In the sense that okay, now this is about bricks, and we always think about bricks in the place, but the problem with Andrea Brides and other brick in the wall, we have made the computations in two different lattices. So the one that is in the picture and the usual one, the 2-1, where the bricks are alternating and the results are different. And in general, these techniques coming, let's say, upscaling from microscopic situation to macro, which I name usually homogenization, so to homogenize, is really strong dependent on the shape. And that is engineers, they work a lot on metamaterials. It's precisely this. You can obtain, by mixing two materials in a certain proportion, in a certain geometry, you can obtain different results. And the geometry is crucial. Thank you for the question.
Other questions? Other curiosities? Okay, maybe I have a curiosity. You said that maybe in the last project, or the one before the last, there are also elastic materials. And how are they integrated, like in the?
Yes.
So
Okay.
how is that this mix? I mean, I'm not in the field, so it's like
Yeah.
curiosity.
Yeah, it means that the condition that the jump can occur only inside the gray region, it is represented as a constraint. So in a sense, your energy is what you expect. So you penalize the smooth deformation and also this H1 of SU means the length of the fracture, but only if the fracture takes place in the gray region and plus infinity otherwise. So it means that it is forbidden to break out of the gray region. So in this way, you represent the fact that out of this V epsilon, you cannot break.
Okay.
And that is elastic.
Thank you. Other questions? No? Okay, if not, then let's thank again Professor Chiadò.
Yeah, if you find out a way to remove this ugly line. This one. Ah, okay, so. Okay, in this slide is all this, yeah. Okay. So I'm happy to have here also Maria Strazzullo. She now is TDA at Politecnico Turin. And she will present regularized feedback control strategies for convection-dominated Navier-Stokes equations, full and reduced models. So thank you, Maria. Actually, we have a niche.
No, nothing.
I will.
You go. Okay, I go. Okay. So thank you very much for the invitation. I'm always happy to be here. I'm happy to see friendly faces here. First of all, I'd like to thank all the organizers for, SISSA Women in Mathematics, and a special thank to Anna that actually put a lot of effort in the slides of today. And she did a great job. I'm proud of you. Okay, great. So let's start with the scientific part. I will talk about actually some kind of stabilization for convection-dominated Navier-Stokes equation in control frame.
You get the slides.
Okay. Okay. So now let me try to introduce the problem with a drawing. So imagine that you are working with a flow that has some kind of vortices inside, but you don't want to see vortices. You would like to see something like that. So a laminar flow at the side state, a stable state. You can do that with control strategies. I work with simulations, okay? So I need some kind of discretization of a continuous model, and if my discretization is not good enough, it happens that you can see some kind of numerical oscillation, okay? So there are some kind of very peculiar algorithms that help you to smooth out stuff, smooth out these numerical oscillations, and in this way, you can reach your desired state in a faster way and in a smoother way, okay? So I will show you actually a new control law for large Reynolds, so for convection-dominated Navier-Stokes equation. I will discuss the role of this kind of stabilization and regularization in the control action and in the convergence towards the desired state. And in the end, I work with model order reduction, so I will talk about a little bit model reduction. So this is a joint work with Professor Valeria, Professor Iliescu, and Professor Claudia. So let's see. Yes, it works. So let me talk about the problem formulation. I work with Navier-Stokes equation. So this is the equation. If you're not familiar with Navier-Stokes equation, you want to find the velocity u and the pressure p in some, let's say, suited spaces. Okay, but I don't want to go into the details, but basically you have your Dirichlet boundary conditions with some kind of inlet conditions, and then you have free flow conditions, okay, on another portion of the domain. You have an initial condition because you want to study the evolution of the system. And there is a parameter that I call nu, that is the kinematic viscosity. Now the parameter nu is related, of course, to the Reynolds number. And the Reynolds number tells you, let's say, the regime of the flow, how the flow is actually how much is convecting. Okay, so if you have a high Reynolds, actually you can have, as I told you, spurious oscillation if you're working with a bad discretized space. That in numerical simulation means if you're working with a coarse mesh. Okay. However, I'm cheating a bit because I talked about control. So here we need to add a term, an additional term that depends on the velocity u and on this big U. So big U is the desired state. So if you remember the picture that I showed you before, it was the laminar flow around the cylinder that I wanted to reach. Okay, so divergence with the side state. Now the question is, how can I choose this additional term? The answer is actually that you need a stabilizing term that allows you to be somehow admissible. It means that the derivative of the discrepancy between your velocity and the desired velocity is always met. This means that in time, you are becoming closer and closer to the desired state, and this is what you want to reach. The starting point was actually this paper on the Kamane of 2000 that proposes a first linear feedback control law, given that I call FA, given by this big F minus gamma u minus big U. So big F is actually the momentum equation for the desired state, while gamma is a parameter that depends actually on the kinematic viscosity. This is important. And basically, if gamma, of course, goes to 0, this means it's a penalization parameter. So if gamma goes to 0, it means that you are not controlling much your system because you are getting rid of a term, okay, in the feedback law. They have a theorem that shows that this law allows you to reach the desired state in time in an exponential way. Yes, the convergence is exponential. However, there are some assumptions. So you see that you have that the parameter gamma that is related to the viscosity has to be greater than some, okay? This means that this is not valid for all the Reynolds numbers. So our question was like, can I extend this law in order to have the exponential convergence for every Reynolds? And the answer is yes, of course, if you change a little bit the control law. So we have another control law that I call here FB. And the new control law has an additional term that is actually still linear in the velocity, but non-linear in the desired field. So it's still linear in U. And the solution of the control system is admissible under this new control law, and the convergence is exponential. So you see that basically here everything is positive somehow, and you have no conditions over gamma that is related to the viscosity and to the Reynolds. So some first numerical results to show you why FB is better than FA. This is the numerical setting we work with from now on. So this is classical flow pass cylinder. You have like an inlet velocity here, okay? Free flow boundary conditions here to the right, and homogeneous Dirichlet boundary conditions on the walls here, so around the cylinder and on the top and the bottom. We are working with Reynolds equal to 1000. Here there are the parameters of the mesh, and this mesh is quite coarse. This means that my discretized space is not good enough to approximate the Reynolds number that I'm showing you here. Okay, this is the finite element pair I work with, nothing very special, all the data of my problem, and the desired state. So the desired state is actually a Stokes problem for kinematic viscosity equal to 1. Now, results in the convergence. So here I'm actually plotting the action of the control laws FA and FB for several value of gamma. Okay, so the control parameter. Here I'm showing that basically the two controls, so the old one is the green one and the new one is the magenta one, for high gamma, so for a great action of the control, the exponential convergence is similar for both the strategies. While if I'm decreasing gamma, okay, it happens something very weird with the old control, okay? Because gamma is not verifying the assumption that I told you on the kinematic viscosity, and so working with high Reynolds in this case, okay, breaks the rule. Here we can see the same results, but let's say visually. So on the top, you see standard finite element code for Navier-Stokes equation on this coarse mesh. And as I told you, you see you will have a lot of numerical oscillation. The simulation is not physical at all. What you expect is some kind of vortex shedding behavior. And on the bottom, you see the simulation of the FA control law. So I'm a bit lazy, so maybe here would be sort of like a movie, but you have to imagine that the control law acts in this way. So you have to imagine that there is a block, maybe here it's better, there is a block moving from the obstacle towards the end of the channel that changes the classical behavior of the PDE, so changes the vortices into the laminar flow. So there is this block that transports the laminar flow all over the channel, okay? Now, you see that if Reynolds is equal to 1000 and gamma is small, the control here is not a stabilizer. You have a lot of numerical oscillations. While with our stronger control, the block is moves, and you reach the stabilizing profile. However, our question is now what happens for smaller gamma? So why I am interested now in looking like very small gamma. As I told you, gamma is somehow a finalization parameter. It indicates the effort you are putting into the system in order to reach your goal. And usually you want to put less effort as possible. Okay, so this is the reason why we want to study smaller gamma. And these are the results for a very small gamma, 10 to the minus 4. And of course, the first version of the control, FA, was not working in this case. It was not working for gamma equal to 1, so not even here. Our strong control is a stabilizer, but still you see some unphysical stuff here at the end of the channel, for example. You have some voids that are not physical here, just up and below the block. At the end of the channel, after a little bit of time of devolution, it happens here, a messy behavior, even if at the end, you reach your desired state. So the next step is somehow to smooth out with some kind of stabilization, regularization, these oscillations in order to reach our goal in a faster way. So I'm going to introduce actually two algorithms that are related to this kind of stabilization. So first of all, I will introduce a ball fit relaxed regularization. So it is a 3 steps algorithm. As a first step, you apply standard control Navier-Stokes equation. So from now on, I'm always working with FB, that is the stronger control that I showed you before. You apply Navier-Stokes equation, you obtain this intermediate velocity, Wn plus 1. So you have a time integration, okay? Once you have this intermediate velocity, you filter the velocity. So here you are applying basically, let's say, an additional viscosity for fake viscosity that you apply to the flow in order to smooth out all the high frequencies of the flow and all the oscillations. However, this parameter here somehow can be over smoothing. And this is the reason why we have a third step that is relaxation. Here I propose a convex combination between the filtered velocity and the standard Navier-Stokes equation of the evolution of the standard Navier-Stokes equation. And in the end, you have a velocity that is smoothed, but somehow has all the features of the flow that you are expecting. And now we have to understand how this algorithm affects the convergence toward the desired state. And we have a theorem, and we were not able, the exponential convergence is not guaranteed anymore. Okay, so this is bad. Indeed, we have some terms. So we have a term that actually goes to 0 if you increase the number of time steps. However, you have some terms that depends on the desired state that it's not guaranteed that they go to 0. So worst case scenario, you can have a plateau during the convergence. And this is the reason why we actually tried to take, let's say, the best from the two theorems with a new algorithm that here I call adaptive EFR. So basically what you do is like you apply EFR until you reach a good agreement in norm with respect to your desired state. Once you have this good agreement, so you have a tolerance tau, once you reach this tolerance tau, you move towards the solution of the standard controlled Navier-Stokes system. In this way, in the beginning, I'm smoothing out stuff. I will reach the convergence faster, and I would avoid the the plateau eventually, and I will recover the exponential convergence because I work with standard Navier-Stokes equation, and we show that if we work with standard Navier-Stokes equation, we have exponential convergence in time. Indeed. So here I have some numerical results about the convergence towards the desired state. Okay. Here you see a lot of parameters. They were, let's say, picked with trial and error. Sorry. Consider. So here we have three lines. The light blue line is the one with no stabilization. And you see that it converges, but it's a little bit bumpy. You can see it also from the logarithmic version of the plot. This is the same plot, but in logarithmic scale. Then you have EFR and the new algorithm, adaptive EFR. And from this plot, they are comparable. But if I look at the plot in logarithmic scale, I see that EFR, as we studied in the theory, has a plateau. While adaptive EFR, of course, it's the same up to a threshold that I decided. Okay. From here on, I decided to work with standard Navier-Stokes equation, so no regularization. And so in the end, we are recovering the exponential convergence. Here, there are some plots about this fact visually. So this is the version without regularization. You see that was the messy plot that I showed you before. And here I have the plots with the regularization. You see that everything is smoothed out, and I can reach, you see the laminar flow better with respect to the other strategy. And now I would like to talk about a little bit model order reduction. So why should I use model order reduction in this context? So imagine that here we are working with Navier-Stokes equation. So I'm working with the convection-dominated Navier-Stokes equation. So I have control also, and I need also regularization. So you see that there is a lot to do, and all these activities are very time-consuming. And this is the reason why I would like to exploit the nature of my problem in order to build a surrogate model, a one-dimensional model, to use this model to have somehow, to be faster and study better my thing. Okay, so now the question is, okay, you apply regularization in the phase where you build your model. Do I need to regularize once again also when I'm working with the surrogate model or not? This is the reason why here I'm comparing two algorithms. They have very ugly acronyms, sorry for that. But when you see AEFR, okay, on the left, it means that I am regularizing in the finite element space for my previous discretization. When you see no EFR on the right, it means that I'm doing nothing on the surrogate model. When you see AFR on the right, it means that I'm regularizing once again also the surrogate model. Okay. So let me talk a little bit about model order reduction in the specific. The goal of model order reduction, as I told you, is to build a low-dimensional framework for your problem. Usually it is a linear subspace of your previous discretization. So I use finite elements, and I want to build a linear subspace of finite elements where I can use galactic projection. Okay, and this dimension, of dimension R, that is much lower than the dimension of the finite elements. Of course, I want to maintain some accuracy. Now, the strategy, as you understood, is actually based on a double discretization strategy. You have your solution, okay, that is a continuous solution. Then you approximate the solution with finite element in my case. I call this solution form, full order model. And assuming that this form is good enough, somehow you build your reduced order model of dimension R, and for a new evaluation of your model, you are solving a smaller system because you project everything in a smaller system, and all the quantities that you need are stored and computed in a first phase that I call offline phase, and then I compute a new evaluation online. Okay? How I build my reduced order modeling, I use POD. POD is a explore and compression algorithm. So you look at the solution for a lot of time instances. And what you do is like you compute the covariance metrics of these solutions that I call snapshots. You retain, you solve an eigenvalue problem on that. You retain the n largest eigenvalues, and the eigenvectors related to that eigenvalues, of course, are spanning a subspace of your finite element solution. You project there, and in the end, you have your surrogate model in this way. If you are familiar with fluids, of course, we are solving a saddle point system. And so we need to use supremiser to guarantee the robustness of Navier-Stokes equation in a reduced setting. Here I've written everything for the velocity, but actually we did the same with the pressure. So we took the snapshots for the velocity, the pressure, and we have the basis. And we apply supremiser stabilization. Okay, so now there is a slide for the first algorithm. So AFR, no AFR, it means that I'm applying regularization during the construction of my model, but I'm not applying the regularization when I'm solving once again the model in the surrogate. So you see that here I'm saying, okay, apply AFR algorithm, take your snapshots, compute the basis, and then solve the controlled projected system. That's it. The second algorithm is AFR, and up to line 5 is equal to the previous one. But now, for the new evaluation in the smaller system, you need once again to apply AFR. Okay, so if your reduced solution is not similar enough to the desired state, apply stabilization, else, otherwise, you solve Navier-Stokes. Results. So here, once again, all the data of the problem at the form level, okay? And here are the data at the surrogate level. So here I'm retaining 20 bases for the velocity and 1 basis for the pressure and the supremiser. So in the end, I'm solving a system that is 22 times 22, okay? Instead of, it was like something around 14,000. And the results. So this is my reference, so the finite element. This is the version where I'm not regularizing online, not regularizing in a smaller system. And you see that there are voids, some recirculations here that it's not good, some recirculation also at the end of the channel. While if I regularize once again, I have a smoother behavior, no recirculation here, so I'm reaching a better convergence towards the desired state. And this is also verified from the relative errors. So here I'm plotting the relative errors between the finite element solution and the reduced solution for the two algorithms. And you see that the blue line, the light blue line, it's always below the orange line. So the double regularization works better. And this is for the pressure, so velocity, pressure, and also with the pressure we had a pretty good agreement. Only here I have a very bad agreement, but it's because the pressure has very small values. That relative error is not a good measure in this sense, but I wanted to show you the same, the properties. Okay, I think that this is the last slide of results, sorry. So convergence plot. The convergence plot towards the desired solution. And you see that if I do not use regularization, green line, I have a very bumpy behavior, very strange behavior in the convergence. While if I use regularization also online, so also on the smaller, on the surrogate model, I have a very good exponential agreement with the convergence, and you see it also in the logarithmic scale. This is the last slide of results. So let me conclude. Okay, summing up, I showed you the difference between two control law for Navier-Stokes equation, and I discussed the role of regularization and how regularization interacts with the convergence towards the desired state. And I worked also with model reduction in the constructive regime with regularization and not. Of course, there is a lot to be done. Most of all, numerical analysis at the wrong level, because all the theorem that we have were at the finite element level. Okay, we are a little bit far from true exponential convergence at the wrong level, even if it was showed by the numerical experiments. Inconsistency between all the parameters that I showed. So now our criterion was, okay, I use some parameters for the finite element, I use the same parameters for the surrogate model, but it can be convenient also use other parameters. And of course, we would like to go towards higher ranges, so two words. Okay, so here acknowledgement, and I actually thank you for the attention.
Thank you very much, Maria. So are there questions from the audience? Nicola?
I have one curiosity. If you were to take a very large number of years ago to construct your basis, is the stabilization necessary also in the use of the pattern or no?
So of course, let me show you that. So here we are retaining actually the 99% of the energy with these modes. Okay, so it's already a high number in the sense that you are already keeping a lot of energy. And I mean, for this problem, the control itself is a stabilizer. Okay, so this problem is easier with respect to standard Navier-Stokes equation in this sense. But even if when you have a good representation of your problem, projection-based reduce of the modeling is based on the model itself. So if the model somehow is turbulent, okay, it's very highly nonlinear, it's a problem for the simulation. So usually the consistency between the models is very useful, even if you are using a lot of basis function. For example, for Navier-Stokes equation, I have a study. We are using something like 100 basis function and still using, you know, the stabilization both offline and online helps a lot.
So it is effective.
Yes, I mean, it helps. It helps. Of course, there is the drawback that you need somehow to, you know, increase the online phase because
Yes.
you need to solve another problem, but it's really modular and it's a linear problem.
Any other questions? Federico?
So two curiosities. So one is so now you showed the control, let's say the desired state is a steady state. Can you do that with, let's say, unsteady states?
Like time-dependent problems. You can do that. I mean, in the proof, everything works fine. So you can have time-dependent problems. With the numerical results, okay, sorry. With the numerical results, we had some issues. You need a time-dependent problems that has less oscillations. Yes, if you go, I mean, that stabilizes in time. You need very small oscillations in order to see actually the convergence.
And second one was related to the fact that so as you said, like, so to build a reduced model, we need usually a nice full order model. So how the performance, or if you tested that, how the performances of the reduced order model in this case are affected by the coarseness of the finite element problem? Like, so how the control system that you are developing is essentially affected by how bad is your initial configuration for the mesh size?
I mean, these results are quite good because the mesh is coarse, but not very coarse.
Yeah, indeed.
Yeah. Okay. So if you're working with a very coarse mesh,
Okay, yeah, sure.
The results would be really bad.
Mhm.
But you can tune all these parameters here.
Okay, so
So you see, here I have something like square root of 11. It's
Oh,
okay, because I worked on the parameters in order to have a pretty good agreement towards the decide state. And this is really tuning stuff.
Oh, perfect. But still, the point is that, let's say, no matter which is the recursiveness of the mesh, then there's hope that, let's say, tuning in a
The
good way,
tuning parameter extension, yes.
it will still, of course, you will not get the same solution as in the hyperdeity case, but still, let's say, you're possibly able,
Yes.
it's possible to stabilize.
I have to admit that I had some tests on very coarse meshes and it was a nightmare. So this is the reason why we moved towards, let's say, a final mesh, not really fine. And in the end, we were able to find the parameters.
Okay.
Very coarse meshes, it's a little bit.
So,
Other questions, curiosities? Nicolò?
One curiosity regarding the theoretical results. Are those, let's say, dependent on the spatial temporal situation or are on the team level?
They depend not on the spatial discretization. So you can use finite volume, you can use, okay, but it depends on the time integration. So you need somehow this. Yes, for example, this results is given by the Euler formula, like implicit Euler formula. So if you have another time discretization, maybe you have some other terms here.
And secondly, like on the results part, you're doing the reducible model just to like the time is the only parameter in the reducible model. You're not doing any extrapolation, it's just like in the range.
Yes,
okay.
but we show that in the reducer of the setting, this is true. It's only reconstruction, but somehow the double regularization helps you in reaching the goal faster. So you are faster with respect, a little bit faster with respect to the.
Yeah, I mean, you already have answers that this right.
Yes, of course. Yes.
Okay.
To sell my. Yes. No, it's only reconstruction. Also because extrapolation is not a good idea here, because you know that in time you reach the decide state. So you know that from t equal to 2 on, you will always have the same behavior. Okay? But this can be useful, for example, if you want to work with controls using different parameters. So you have the snapshots for some parameters. Yes, exactly.
For no standard that totally makes sense.
Yes, but not only, also for gamma, for example. The gamma is the parameter that you need in order to control your system. So here you can perform some kind of parameter estimation.
Like gamma as much as possible, like if you can avoid the whole full model time, for example.
Yes. This is a possibility.
That's
I have like a question. In the relative errors for the ROM, I saw, maybe I saw wrong because it was. No, so the relative errors, we have the same issue in our project. I mean, so in this case, there is no regularization for pressure dedicated.
No,
just for the velocity, right?
Yes.
Okay.
No, we are not taking care of the pressure here. It's like, okay, let's see what happens to the pressure.
Okay, do you think there may be a regularization for the pressure in hell?
No, I don't know. Because actually there is no, there is no theoretical, as you know, there is no theoretical study about the regularization of the pressure. Usually you do not regularize the pressure, only the velocity. You filter only the velocity. You smooth out only the velocity. Because you are working with weakly divergence free stuff, and so no one cares about pressure, but.
Okay, thank you. So I think we can start here. So let's thank again Maria. Nice talk. Okay, so I would like to thank you all for being here today, and thanks also to our speakers for accepting the invitation to be here. And so we will see each other hopefully in the next SISSA Women in Mathematics. So.